Okay, welcome back. This is now 8.7. I'm going to skip 8.6 because it's basically just looking up things in a table. And the truth is, it seems, at least to me, that that's kind of obsolete given the algebraic computing systems that we have now. You just go for 8.6 type stuff, just go to Wolfram Alpha, I guess, Wolfram Alpha, and they'll have a place where you could type. I mean, it's an integrator. There's tons of integrators online, but if you type in basically int, which means integrate, and then put your function that you're trying to integrate in right here, and then push comma, type comma, and then either just write x, which will give you the indefinite integral, or type x equals a dot dot to b, whatever your bounds are on your integral, or your limits are on your integral, and then end parentheses. That thing will output the integral of pretty much anything you want. Okay, so I'm sure there's still holes in the integrator somewhere, but I'm not aware of them, and I don't know anybody who would use a table for any situation. So for 8.6, I can sum it up in this one line of code that you would plug into the website for Wolfram Alpha. So just go to Wolfram Alpha, in other words, Google Wolfram Alpha, it'll pop up, and then you could type in this and the menu, and it'll pretty much integrate anything you want to integrate. Okay, so there's that. Our college has Mathematica and Maple as well. And both of those will do integration, but it's much quicker just to go to this website and type that in and get your answer. Okay, so that's 8.6. 8.7 now is going back to doing limits, because in 8.8 we need to do these things called improper integrals, which will require these types of limits. Okay, so 8.7 is indeterminate forms and L'Hopital's rule. Okay. So what are indeterminate forms, and what did we learn in Calc 1? Usually in Calc 1, we would just use some tricky algebra, right? We're explaining the fact that some functions are equal to other functions everywhere, maybe at one particularity, right? And then we could do some algebraic simplification and figure out the limit via substitution. So those cases that you saw were usually called 0 over 0 forms. And for example, we had the limit as x goes to 5 of x squared minus 25 all over x minus 5. Okay. So if you try to do a substitution and you plug 5 in here, you get 5 squared is 25 minus 25, which is 0 in the numerator. Down below, 5 minus 5 is 0, so you got a 0 down there as well. This is indeterminate. Okay? And in Calc 1, we learned how to deal with this issue by replacing this function with a function that's exactly the same at all places except at 5. And that particular function can be found by factoring. So x squared minus 25 is the same as x minus 5 times x plus 5. Then we can remove the common factor, and we just have the limit as x goes to 5 of x plus 5, which now you can do a substitution. 5 plus 5 is 10. Right. So that was our Calc 1 remedy. We had some pre-calc remedies, which I'm going to kind of just absorb into this kind of chop method that I teach students. Okay, so what is that chopping method? If you have some type of infinity over infinity where the numerator and denominators are rational functions, so if, for example, the limit as x goes to infinity of x squared plus 2x minus 5 all over x plus 2, you could figure out this limit just by chopping everything except the high degree terms off. Okay, so this will be the same as the limit as x goes to infinity of x squared over x. Okay, and so that will be the limit of x as x goes to infinity. So you could either think numerically or graphically here. Numerically, as x goes to infinity, 10, 100, 1,000, this function, which is our y equals x, that also goes to infinity. So this will be positive infinity. So this is numerically, graphically, what you're looking at is the y behavior of this graph as x goes to infinity. So this is the graph of y equals x, which is this guy right here, y equals x, the diagonal. And then we want to know what happens to the y values as the x values go to infinity, and they just go to infinity. Okay, so that will always work for you. Let's look at another one. The limit as x goes to infinity of 3x squared plus 5x to the 7th minus 2x all over 2x to the 7th plus 5x to the 5th minus 2. All right, so what you do again, this limit will be the same as the limit of the ratio of the high degree terms. Be a little careful because this wasn't written in descending degrees, right? So this limit, the limit of this thing is equal to the limit of 5x to the 7th all over 2x to the 7th. And then that will be the same as the limit as x goes to infinity of 5 halves, which of course is just a constant. The limit of a constant is the constant, it's 5 halves. In short, it's very important to kind of have under your belt how to deal with limits of things like this, right? 1 over x to the 5th. So if the denominator is just getting bigger and bigger and bigger and the numerator is kind of staying constant, this will always go to 0. Okay, so its form is L over something going to infinity. And that form will always end up being 0. Okay, so if you have a constant over infinity, that will always be 0. So hopefully then you can agree the limit as x goes to infinity of 1 over x, well, that's just going to be 0 as well. So pretty much the limit of 1 all over x to any power that's positive is going to be 0. Okay, even 1 over square root x, that's still going to go to 0. Slower than this, but it will still get there. Okay, more examples then. Here we have the limit of 3x cubed minus 2x squared plus 1 all over 5x cubed minus 3x plus 5. And we're going to x to infinity. Right. So I haven't been noting it, but the form is infinity over infinity at this point. Cubic functions will go off to infinity or negative infinity depending on the leading coefficient. If it's positive, its behavior is like that. It's going to positive infinity as x goes to infinity. That'll be the same for this. It's also going to infinity. But in general, if it's infinity over infinity or negative infinity over negative infinity or negative infinity over positive infinity, whatever, you can use this rule with these rational functions. So this will turn into the limit as x goes to infinity of that over that. Right? And when you simplify that over that, you get 3/5. So it's just equal to 3/5. What else? Let's look at another one. Example. You have the limit as x goes to infinity of 2x plus 5 all over x cubed minus x squared plus 2. Okay, so this will behave the same as the limit as x goes to infinity of 2x over x cubed. 2x over x cubed is the same as 2 over x squared. And then we already noted this type is L all over infinity, which will always be 0. Alrighty then. So what's new? What's new is L'Hopital's rule. how does this work? So if it's theorem 8.4 in the book, but if you have the limit of a ratio of two functions, f of x and g of x, and its form is one of these indeterminates, 0 over 0, infinity over infinity, or some plus or minus infinity over plus or minus infinity type. Then you can evaluate the limit by taking the derivative of the top and the derivative of the bottom and doing just figuring out that limit. This thing is equal to the limit of f of x over g of x. Should have wrote it in the other order. But you could do that assuming that this thing here exists. Or it's infinite. Okay. Okay. You could do a minor proof of this. They have a better proof probably in the book, but an easy kind of example of this panning out for us. Suppose f of a equals f g of a, which equals 0. And then f prime and g prime are continuous. And this g prime of a does not equal 0. In that case, you can write the limit as x goes to a of f of x over g of x as the limit as x goes to a of f of x. And then because f of a is equal to 0, sorry, around a room there's somebody who's listening to the stupid phone. The limit of this thing is equal to then the limit of f of x minus f of a, because f of a is equal to 0. So you can add or subtract that in, it won't make any difference. And same for the denominator. So why do I care? Well, this has kind of the flavor of our alternative form for the derivative, right? So I could rewrite this by multiplying top and bottom by x minus a, and the result will be kind of the derivative of f at a all over the derivative of g at a. So you note, again, derivatives are basically just slopes, limits of slopes. And that's what we have here, a ratio of these slope formulas. And so each one is basically the derivative of f with respect to x. And on the bottom, it's g prime of x. And then if you substitute in a, you get f prime of a all over f prime, g prime of a. Okay. So at least in this case, it kind of looks, clear that you can do this replacement. The limit of this is equal to the limit of the derivatives, and then evaluate this thing, and that will be the limit of this guy here. Okay. Okay, so that's just a simple case again. I stole that proof from Stewart. Okay, let's get back to the homework problems and reality in general. 11, limit as x goes to 3 of x squared minus 2x minus 3 over x minus 3. Okay, so first identify the form. It could just be determined. You could just do a plug and chug sometimes, right? But in this case, it's 0 over 0. 9 minus 6 minus 3 is 0. 3 minus 3 is 0. So what am I going to do? I'm going to do L'Hopital's. So you can only do L'Hopital's if you have one of those particular forms I showed you. Okay, so here I'm approaching 3. I take the derivative of the numerator. It's 2x minus 2. The derivative of the denominator is 1. If you plug 3 into this expression, you'll have 6 minus 2, which is 4. Here's the limit as x goes to 0 of the square root of 25 minus x squared minus 5 all over x. So the point is, in Calc 1, you probably were able to do these, right? In this case, you would factor and remove. In this case, you would rationalize the numerator, right? Let's check it. Plugging in 0, I have square root of 25 minus 0. Square root of 25 is 5. 5 minus 5 is 0. Plugging 0 in for x, I get 0. So it is qualifiable as a L'Hopital's rule. And let's take the derivative. So the derivative of the numerator portion, 1/2 times 25 minus x squared to the negative 1/2 times negative 2x. And then the derivative of 5, 0. And then that's all over the derivative of x, which is 1. So this is not the quotient rule, folks. This is different. You're taking the derivative of the numerator and then taking the derivative of the denominator separately. Okay, let's clean this up. I'll have apparently negative x all over 2 times the square root of 25 minus x squared. Doing a substitution this time, I get 0 over 2 times root 25, which is 2 times 5, which is 10. So 0 over 10 is 0. Let's look at number 19. So I have the limit as x goes to 0 of sine of 3x all over sine of 5x. Doing a substitution, sine of 0 is 0, sine of 0 again is 0, so it's 0 over 0. I do L'Hopital's. The derivative of sine 3x is 3 cosine 3x. The derivative of sine 5x is 5 cosine 5x. And then try another sub. So subbing in this time will just give you 3 times 1 all over 5 times 1, in other words, 3/5. Okay. Using this method of L'Hopital's, you can attack other indeterminate forms. Okay, so section 3, there's basically 3 other types that we should be able to do after this section. So other indeterminate forms. And the first one is 0 times infinity. Okay, so the procedure is rewrite it as a complex fraction. So maybe something like 1 over 2 is the same as 1 over 1 over 2. It's that idea. Secondly, then you'll apply L'Hopital's. Okay, so let's take a look here. I have 45. The limit as x goes to infinity of x times sine of 1 over x. Okay, so identify the form. If I put infinity in for x, it's going to go to infinity. Okay, so this part is infinity. If you put something at infinity for 1 over x, that'll be L over infinity, which is 0. And then you're taking sine of 0. So sine of 0 is 0. So the overall form is infinity times 0, which is this form. Okay, so the program is, say, rewrite it as a complex fraction. So that's what I do. X is the same as 1 over 1 over x. So I can write this expression as sine of 1 over x all over 1 all over x. Okay, so I'm just rewriting x as 1 over 1 over x. And there it is. Okay. Now I'm going to do L'Hopital's rule. And I have then the limit as x goes to infinity of the cosine of 1 over x times the derivative of 1 over x, which is negative 1 over x squared, all over the derivative of 1 over x down here, which again is negative 1 over x squared. Negative 1 over x squared and all over negative 1 over x squared, those factors will cancel out, and you're just left with the limit as x goes to infinity of the cosine of 1 over x. Okay, so as x goes to infinity, 1 over x goes to 0, and then cosine of 0, we all know, is just 1. Okay, the next type then is sort of has exponents involved, so it'll be something like 1 to infinity, infinity to the 0, or 0 to the 0. Okay. Okay, so the ultimate version of this is this guy, the limit as x goes to infinity of 1 plus x to the 1 over x. We all know this, or some of us know this, is going to equal e, right? Right, so how do we figure this one out? It's, if you do an input, it's infinity to the 0 power right now. So you could do this method to it. And the trick is, and I do it a little differently maybe than the book does, but the methods are equivalent. I'm going to rewrite this as e to the ln of this. Okay, so it's e to the ln of 1 plus x to the 1 over x. Then I use the power rule to bring the 1 over x down in front. So I have the limit as x goes to infinity of e to the 1 over x times the ln of 1 plus x. Okay. And then I'm going to slide the limit up into the exponent. So I'll end up with e to the limit as x goes to infinity of 1 all over x times the ln of 1 plus x. And then you just figure out this limit, and at the end, e to whatever that is your answer. So this thing right here, as it sits, 1 over x as x goes to infinity is a 0. And then ln of 1 plus x as x goes to infinity is infinity. So it's actually 0 times infinity form up here. So the deal with that is to rewrite it as a complex fraction. In this case, it's kind of already rewritten. Okay, so maybe my directions in the last example weren't 100%, right? Couldn't exactly put that into a computer for cases like this. If you rewrite it as ln of 1 plus x over x, the form turns into infinity over infinity, and then you could do a L'Hopital's on it. Okay, so this now is a form infinity over infinity, so I could do a L'Hopital's in the next step and rewrite it as e to the limit as x goes to infinity of the derivative of ln of 1 plus x is 1 over 1 plus x. Of course, the derivative of x is just 1. So I have the limit as x goes to infinity of 1 over 1 plus x, which is e to the, this will become 0, right? Because it's L over infinity. So it's e to the 0, which of course is, well, I guess it's 1. I thought this was equal to e. Yeah, bummer. Yeah. Maybe the one that's equal to e is the one where x is going to 0 or something like that. That'd be 1 to the infinity. Oh well, let's move on. Look at another one. The last form is where you have an infinity minus infinity type. Now, infinity plus infinity is actually determined, is not this indeterminate form. Infinity plus infinity is infinity. It's only when you have kind of this competition between positive infinity and negative infinity that you have to work with L'Hopital's. And usually, and I say usually because we saw in this last example, it's not always going to be the case. Usually what you do is combine into one term and then use L'Hopital's. Okay. So let's look at 59. And we have the limit as x goes to 1 from the right of 3 all over ln of x minus 2 over x minus 1. Okay, so I'm going to combine these guys in the one term. I mean, you should make sure that they actually are of this form, right? So we should at least do that. As x goes to 1 from the right, so it should be 0. Well, yeah, as x goes to 1 from the right, the ln of x is getting really, really close to 0. Okay? So it'll be 0 positive. In other words, this is infinity. So I have 3 over 1/10, 3 over 1 millionth, 3 over 1 billionth. And those will be complex fractions. When you do the reciprocal, it's going to be like 3, 30, 300, 3,000, 3 million. Okay, so this guy then is L over 0. So you know it's either positive or negative infinity is what I'm getting at. So if you do a test value like 1.1, it'll be positive over positive. So it's minus a positive infinity. In other words, infinity minus infinity. Okay. So if you've forgotten, how the heck do you figure out the limit of 2 all over x minus 1? Whenever you have a form L over 0, that's either going to be plus or minus infinity. Okay, I know it's infinity via a test value, so you can just do a test value, and we're approaching from the right, so you consider a value like 1.1 and plug that into here, and it'll be positive all over 1.1 minus 1 is positive, so this is positive infinity. Okay, and because it's subtracted, it's minus infinity. But if I was just looking at the limit on its own, this part would be positive infinity, infinity. Okay, so I need to find a common denominator, long story short. Okay, so I'll have 3 times x minus 1 minus 2 times ln of x all over x minus 1 times ln x. Okay. If you do another substitution, you'll have 0 in the denominator. In the numerator, you'll also have 0. Okay, so it's a 0 over 0 form now. In other words, you could do L'Hopital's. Okay, so once it's in that form, apply L'Hopital. So I have this equaling the limit as x goes to 1 from the right of 3x minus 3. The derivative of that is just 3 minus the derivative of ln x is 1 over x, so 2 over x, all over x ln x. So doing a product rule, I'd have ln x and then plus x times 1 over x, which is 1, and then minus 1 over x. Okay. So this is a bit of a mess. Let's rewrite the heck out of it, if possible. So this is the limit as x goes to 1 from the right of 3x minus 2 all over x times the reciprocal of this junk. So that's 1 all over, if I find a common denominator there, it's going to be x. And then if I do its reciprocal, the x is going to flip into the numerator. But as it sits, it'll be x ln x plus x minus 1. Okay? And then these guys will divide out, and I'll be left with the limit as x goes to 1 from the right of 3x minus 2 all over x ln x plus x minus 1. Recheck its form. If you plug 1 into there, you'll have an L in the numerator. If you plug 1 into the denominator, you'll have 0. So it's either going to plus or minus infinity. You could do a test value to figure out which one. So plug in 1.1. So 1.1 minus 1 is positive. 1.1 times ln of 1.1 is also positive. Positive plus a positive is positive. So it's positive infinity at the end of the day. Urg, right? Okay, maybe do one more, just for the sake of giggles. Let's look at number 55. And I have the limit as x goes to 1 from the right of the ln of x to the x minus first power. Okay, so this is the form 0 to the 0 power. And you could do this method. So I'm going to rewrite it using an exponential. It'll be e to the ln of x to the x minus 1. I'm going to do a power rule, bring this down. I'm going to move the limit into the exponential. So I have e to the limit of x minus 1 times the ln of x as x goes to 1 from the right. Okay. The ln of 1 is 0. I'm coming in from the right, so the ln of that is infinity, and then this is 0. So the form is actually 0 times, well, in this case, negative infinity, but we'll just say infinity. Okay. So I need to rewrite it as a fraction. So I have then e to the limit as x goes to 1 from the right of ln of x all over 1 all over x minus 1. So now the form is infinity over infinity, and I can do L'Hopital's. I don't know how much of a help that's going to be, but we'll look. x goes to 1 from the right. The derivative of ln of x is 1 all over ln of x times 1 over x. So it would be 1 all over x ln x. And then that's divided by the derivative of this thing, which will be negative 1 all over x minus 1 squared. Okay, so multiplying by the reciprocal and seeing what I have the e to the limit as x goes to 1 from the right of, I guess, negative x minus 1 squared all over x ln x. This form is still 0 over 0, so we can do L'Hopital's again. There's no rule against that. So it is 0 over 0. Let's do another L'Hopital's. So on the numerator, it'll be negative 2 times x minus 1 to the first power. In the denominator, I got to do a product rule. So it'll be x times 1 over x, which is 1, plus leave x alone times, leave ln of x alone, and so you get ln of x, 1 times ln of x. Okay, now it's no longer that 0 over 0 form. If you plug 1 in, certainly in the top you get 0, but in the bottom you're getting 1. Okay, so ln of 1 is 0, 1 plus 0 is 1. So now it's just 0, e to the 0, and then e to the 0 is 1. So the limit of that guy turns out to be 1. Thanks for watching.